Okay, let's try to look at the third example of line integrals conservative vector fields. So let's find the work done by an inverse radial force from P1 to P2. And this will be for a distance of D1 and D2 from the origin. As it turns out, these will be the only thing that matters. So the force in question, it'll be kr divided by r squared. So notice it's radial. So it only points out from the origin. And it turns out this is actually conservative. It turns out we can write f as the gradient of some function which only depends on r, the radius. And I'm abbreviating this as the length or magnitude of the position vector. Okay, so let me show you why. By the chain rule, this is f prime of r times the gradient of r. Therefore, because r is the square root of x squared plus y squared plus z squared, the gradient of this thing, it'll just be x, y, z divided by that square root. So in other words, we get r divided by little r. So overall, we get f prime of r divided by r times the position vector. So now let's equate these two things. So in other words, k times the position vector divided by the radius squared. Let me just write little r so it's less cluttered. This will be equal to f prime of r times the position vector. So therefore, if we equate these two things, k divided by r squared should be f prime of r over r. In other words, f prime equals k over r. We conclude f is k times the logarithm. So in other words, our vector field is the gradient of k times the logarithm. So it's a conservative vector field. And if you're given, for example, cubed, you can follow the same procedure to deduce what the potential function is. So why is this useful? It turns out this is all we need. Notice that this only depends on the radius. As long as we're given these distances, we're essentially done. Let me show you why. So the work, it's f dot dr, force times displacement. We know it's the gradient of some function. So if we apply the fundamental theorem, we get f at p2 minus f of p1. But remember, our f is a function only of the radius. And so p2 corresponds to d2. p2 has distance d1. Let me draw this out. p2 and p1 have distance d2 and d1. So that means this is f of d1 and d2. So we get k logarithm d2 minus k logarithm of d1. And this is the work done. So just as a sanity check, in case an expression for f is slightly different, notice this increases. with D2. So the work done to move it, it's actually positive, so it increases energy. And this makes sense. So the force is outward pointing. And D2 is farther. So the force moves along the displacement. You're increasing energy as a result of this. If P2 were down here and P1 were up here, you would actually be losing energy because you would be going against the force. So this is a sensible result. Okay. Thanks for watching.